My project is the parametric study of selective laser melting process for stainless steel 316. The selective laser melting process utilizes a heat source to melt the metal powder layers to fuse the metal particles. The material is then cooled to solidify, thus creating a solid 3D part. All additive manufacturing processes have parameters that can be modified to alter the quality of the fabricated parts. The process parameters can be categorized into four main areas: laser, scan, powder, and temperature. Literature review was conducted to gain insight on how parameters can impact the SLM process. Several studies found a strong correlation between the residual stresses formed and the final fabricated part, as the samples had higher yield strength but lower elongation percentage factor than conventional manufactured parts. Another study found high porosity and large pore size can reduce ductility, whereas fine grain size and high dislocation density improve its mechanical strength. The residual stresses formed by the thermal process of SLM can be controlled by the process parameters. One study found that laser power and spot size influenced the center track width of the molt pool, whereas the scan speed affected the remelt zone and wetting angle of the molten track. Another study found the substrate temperature influenced the part density and dimensional accuracy. It is important to note that these relationships between the parameters and the properties are based individually. Further research is required to optimize the SLM process of metals based on the influence of a collection of process parameters. The objective of this project is to optimize the mechanical properties of SS316 specimens based on the selected parameters of SLM process. The process parameters to be analyzed in this study are scan speed, spot size, diameter, and substrate temperature. Several major deliverables are to be presented for this project. First, a MATLAB script file will be delivered by October 2020, which is used to calculate the heat transfer involved in the SLM process between the heat source and the material. Since the process parameters are the design variables, the computation will undergo numerous iterations which can be accomplished with this software. By December 2020, FEA results will be presented simulating mechanical loadings applied on the final specimen by a universal tensile machine. The max von Mises stress, equivalent strain, and strain energy are to be calculated using ANSYS software. By December 2020, 3D response surface plots and statistical plots will be presented to show which combination of parameters will yield the maximum mechanical properties. The response surface plots will be generated based on the theoretical results from MATLAB and the simulated results from ANSYS. The output variables, which would be the mechanical properties, will be plotted along the z-axis, and the input variables, which are the process parameters, will be plotted along the x and y axes. Both regression and residual plots are to be generated based on the theoretical and simulated results. Since the objective is to optimize the SLM process of SS316, the maximum mechanical properties can be achieved by altering the SLM process parameters. The optimal mechanical properties generated from these parameters are located at the maximum vertex of the response surface curve on the plots. Analysis of variances method is used to evaluate the FEA results. Regression plots between the simulated versus theoretical quantities should have a relatively high coefficient of determination, which indicates the percentage of variance between the output and input parameters. The residuals plot assesses if the following model is unbiased, where the following results should display randomness. Finally, physical specimens are to be fabricated using optimal process parameters that would yield the maximum mechanical properties in order to validate the results of the simulation. The mechanical properties of the physical simulated specimens are to be compared with minimal error. The temperature change in the heat transfer model can depict how thermal energy is applied on the material. The heat transfer model can depict how the thermal energy is applied on the material during the SLM process. During the process, the phase of the material changes from solid to liquid and then back to solid. Since the heat conduction primarily affects the phase transition, heat convection and radiation can be neglected. The general 3D heat conduction equation, which is treated as a partial differential, will be used to model the heat transfer of the SLM process. The temperature equations are a function of time in all three Cartesian coordinate directions. Due to the phase transition, the material properties are dependent on temperature. Gaussian approximation is used to represent the energy absorbed by the laser as it travels along all three directions. FEA will be conducted based on the results of the heat transfer to model the specimen of the simulation. As well, ANSYS contains an additive print software package that offers FEA specifically for additive manufacturing applications. A major challenge anticipated for this project would be the impact of COVID-19. Although a majority of this project is primarily focused on the simulations, which can be conducted at home, access to fabricate the specimens on campus in the upcoming semesters are still up in the air. A possible alternative would be to obtain the specimen samples by an additive manufacturing service. The manufacturer would fabricate these specimens with the required process parameters established. The preliminary work done for this project was to develop a MATLAB pseudocode to compute the partial differential heat transfer of the SLM process. The material properties of SS316 powder, range of process parameter values, initial and boundary conditions for the partial differential equation were initialized. Several function script files are intended to be called to compute several components of the differential equation, such as the energy absorbed by the laser and the material property functions. Another preliminary work done was the setup of the tensile test FEA simulation, where the dimensions of the specimen conform to the American Society for Testing and Materials standard. The setup of the FEA was established using arbitrary values. A fixed support was placed on one end of the specimen, and a 7,500 Newton tension load was applied on the opposite end. As expected, the maximum volumetric stress occurred near the center of the test specimen. Several resources needed for this project will be obtaining professional licenses from MATLAB and ANSYS. By September 2020, I will need to obtain confirmation that a 3D printer will be available for students in the upcoming semesters. If so, then I can begin gathering the 3D printer specifications and ensure that the device is operational when I am ready to fabricate my specimens. For the second semester of this project, I should obtain access to the universal tensile machine available in the engineering lab on campus to conduct the tensile tests on the fabricated specimens. An optimized SLM process is another improvement for additive manufacturing in future industries. For example, NASA 3D printed a rocket engine fuel pump that successfully rotated 90,000 RPM under harsh conditions. The fuel pump that was manufactured had nearly half. My project is the parametric study of selective laser melting process for stainless steel 316. The selective laser melting process